In this next section, 2.5, we'll be looking at measures of position. And positions just mean how far into a set of data does a data value occur. So does the data value occur close to the front end, close to the low end? Does it occur close to the high end? Does it occur somewhere close to the middle? So just how far into the set of data will you find that particular value? When we talk about measures of position, quartiles and percentiles are commonly used um, terms. If you have a dollar that's 4 quarters, often we break things into different quartiles. The first quartile, the first quarter, is just the first 25% of the data. The first quartile or the 25th percentile are the same thing. And what that means is about 1/4 or about 25% of the data is at that level or below it. So if we have a set of data, we have a list of data points. The first quartile is a place where about 25% of the data is from there down. The second quartile, if you have 2 quarters, you have 50 cents. So that's equivalent to the 50th percentile, which is the location where 50% of the data is at that level or below. That's also known as the median. Remember, the median is the middle of your data. And we don't mean halfway between the smallest and the largest value, but when we say median, we mean we have the same number of data points below as we do above. So the third quartile is the position in our data where 3/4 or 75% of the data falls at that value or below it. So they give us an example here. They give us a list of values, and in this case 25 is the median. That's you have the same number of data points below as you do above. That's also the second quartile. In this bottom half, if we cut the bottom 50% in half, then this would be the middle of that section. So from here down, that's about 25% of the data. So that's the first quartile. If we take the upper half and cut it in half, then that leaves about 25% from here up, which means you have about 75% from here down. So that's the 75th percentile or the third quartile. You have about 3/4 of your data at this level or below. So they give us another example, and it says to use technology with this data to find the quartiles, but we're going to do this by hand. It'll be good practice to see how to do this. So first of all, we need to know, well, how many pieces of data do we have? So here's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 25 pieces of data. And let's do a stem and leaf display so that we can find 20s, 30s, 40s, and 50s. So a 50, a 52, a 51, a 49, 52, 51, 5, 41, 47, 36, 30, 44, 40, 35, 40, 45, 34, 33, 23, 34, 27, 16, 18, 18, and 35. So now let's put those in order. So the first row is in order. The second row we would do 3, then 5, then 7. The third row we would have 0, then a 3, then 2 4s, then 2 5s, and a 6. Then the next row we have 2 zeros, and a 1, a 4, and a 5, and a 7, and a 9. And the last row we have a 0, 2 1s, and 2 2s. So we have just taken our data and we put it in order from smallest to largest. Okay. So 25 pieces of data. So let's find our quartile. So the first quartile, also known as the 25th percentile. So we need to know how far into our data does that occur. So we need to find out if we have 25 pieces of data, how much would be, or what is 25% of the 25 pieces of data that we have. So how many pieces would be 25% of 25? So 25% times 25, we can pull out our calculator. 25% of means multiply times 25. So we get 6.25. So it takes 6.25 pieces of data to make up 25% of our data. Well, what does that mean? So the 6.25 helps us know the amount of data that is below the first quartile. If this number is a decimal, we're going to round up to the next integer. So our depth will be 7. So as we count into our data, the 7th data value is going to be at the first quartile position. So this is the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. So 30 is our first quartile. So at the level of 30, from that number on down, that will be about 25% of our data. Now keep in mind that with certain sample sizes, in this case 25% is not actually an integer value. So we may not have, if you count how many numbers are below that and turn that into percent, you're not going to get exactly 25%. Some books will say that at the level of the first quartile position, at most 25% of the data is below, and at most 75% of the data is above. And that just has to do with if you have certain amounts of data, you might not get exactly 25% on one side and 75% on the other side. But probably one of the biggest parts here is if this is a decimal, we round up to get our depth. Well, what if it's not? What if this is an integer? If when we calculate this, if we get an integer, then we add 0.5, and that will be how far into our data we go to get our percentile or our quartile. So 8.5 means that our depth, our quartile, will be between our 8th and our 9th position. So if we counted found the 8th piece of data and the 9th piece of data, our depth or our quartile would be halfway in between those. For this particular set of data, When we calculate our quartile, I believe all of them will be a decimal when we round up. But again, for some sample sizes, when we do this calculation, if we get an integer for our depth, then we go halfway between that number and the next. So while we're here, let's go ahead and find the second quartile, also known as the median. So the second quartile, the median, another name is the 50th percentile. We need to find out where is 50% of 25 pieces of data. So 50% of 25 pieces of data is 12.5. Since that's a decimal, then our median, or our second quartile, will be at the next largest integer. So if we count to the 13th position, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, that will be our second quartile. Now for our third quartile, which is the 75th percentile, we need 75% of our data. So if we do 75% of 25 pieces, that's 18.75. That's not an integer, so we round up. So our third quartile will be at the 19th piece of data. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that's our third quartile. So those are our first, second, and third quartile for this particular data set. After we look at our quartile, then we have something known as an interquartile range. We've already talked about what a range is. The interquartile range is the difference between the third quartile and the first quartile. That's basically the width of the middle half, or the middle 50% of the data. Not width, but width. The range is how wide is all of our data. The interquartile range is how wide is the middle half. So in this case, the third quartile is 47. The first quartile is 30. So the middle half of our data has a range of about 17. Sometimes that's shortened as IQR for interquartile range. So if we look back over here, there are some notes about the interquartile range. It's mentioned it's the how much variation or the width of the middle half. Talks about how we calculate it, we just talked about. Now that's often used to find things called outliers. So outliers are values that are outside what is considered to be normal. So to find outliers, we have to find our first and our third quartile, and we get our interquartile range. And then we're going to multiply our interquartile range by a factor of 1.5. So that's basically going to give us a number that is 50% more than our interquartile range. So let's do that with our value here. So our IQR is 17. So if we do 1.5 times our IQR, that's 1.5 times 17. We get 25.5. So what are we going to do with that? So once we get that number, to find outliers, An outlier we're going to consider to be any number that is lower than that amount below the first quartile, or if we add that 25.5 to the third quartile, anything that is above there is an outlier. So let's do that. So our first quartile minus this 1.5 IQR, our first quartile is 30. This value we calculated 25.5. So if we have a number that is lower than 4.5, that would be an outlier. Notice our lowest value is 16. So we don't have an outlier on the low side. Let's look at the high side. Let's see, do we have an outlier on the top end? So if we add this 25.5 to the third quartile, so our third quartile is 47. I believe that would be 72.5. So if we had a value above 72.5, that would be an outlier. But notice in this particular set, there are no values above 72.5. Our largest value is 52. So sometimes we have sets that have excessively large numbers, and when I say that, I mean values that are just not in the normal pattern. An example that we use sometimes is we might have a business and everyone that works at that company might make $27,000 a year. All the employees do, and let's say there are 10 employees. And then the boss might make $230,000 a year. Now, we could calculate a mean. We have 27,000 10 times, and then we have 230,000 one time. And if we divide that by the 11 total workers at this company, the 10 employees and the one owner, that would be what? 270,000 plus 230,000. So 270,000, just in case you're unsure what I did there, that's the salary, the combined salary for the 10 employees, plus the salary of the owner. If we divide that by 11, then he might advertise that the average salary for his company is $45,450, and he might round up to $45,455. And as far as a mean, yes, that is the mean salary for his company, but I'm sure those 10 employees that are only making $27,000 don't take too nicely to the advertisement that people on average make $45,000. That's not far from being twice what everybody makes other than the boss. So this 230,000, that's an outlier. That is, did I spell that correctly? Yeah. Notice it's telling a lie. It is outside of what is normal. Now that's not why they consider an outlier, but anyway, it is a value that skews the mean. It is an exception other than what is normal. So just go back to review. For our purposes, we're going to consider an outlier in anything that is more than 1.5 IQR above the third quartile or 1.5 IQR below the first quartile. Anything outside that region is going to be an exceptional value, so not normal, so an outlier. And one thing that we do once we get our quartiles, sometimes we use our quartiles and stuff to make what is known as a box and whisker display. The box and whisker display uses what is referred to as the 5-number summary. The 5-number summary is the lowest value, the first quartile, the median, also known as the second quartile, the third quartile, and then the highest value. So for our previous example, 16 is the lowest, 30 was the first quartile, the median was 36, 47 is the third quartile, and the highest value is 52. So that's our 5-number summary. A box whisker display is a visual representation of that. If we make a scale, let's go 10, 20, 30, 40, 50. A box and whisker display consists of a box and whiskers. The box is formed between the first quartile and the third quartile. So at 30, we're going to put a line. At 47, we're going to put a line. And we're going to draw a box that starts at the first quartile and goes to the third quartile. And then we're going to put a line at the median. From the lowest value to where our box begins, we're going to draw a line, that's a whisker. And from our third quartile to our maximum value, we're going to draw a line, that's going to be a whisker. So we have a box, and then we have 2 whiskers. This is the lowest, the first quartile, the median or the second quartile, the third quartile, and then the highest value. Now recall what quartiles are. It breaks our data into quarters. So there is the same amount of data in each of these sections. That's the first quarter, that's the second, that's the third, and that's the fourth. There's the same amount of data in each one of these regions. Notice that region, that quarter is narrower than some of the other ones, so the data is more tightly grouped here, where this quarter is the widest, so data in this region is spread out more. So this just helps us to visually see how our data is distributed, how it is spread out. The box is our middle half of our data. The width of our box is our interquartile range. And then we can see the edges, our first and our last quarters. So that's a box and whisker display. The other topic in this section deals with what is referred to as a z-score or a standard score. And what a standard score or a z-score is it is a measure of the number of standard deviations a value is from the mean. How many standard deviations is a particular number from the mean? So, for example, if we had a set of data and the average is 75, and we have a standard deviation of 6, let's look at the data value 87. So 75 is here. If we go 6 more, that gets us to 81. If we go 6 more, that gets us to 87. So 87 is 2 standard deviations above the mean. Well, that one wasn't so bad because the distance from 87 to 75 was a multiple of 6. We just did that visually, but we took how far 87 is from 75, and then we said, okay, that's 12 units away. How many standard deviations is that? So if I want to know how many 6's that is, we divide it by 6, and notice we get 2. So the deviation divided by the standard deviation. So that tells us how many standard deviations we are from the mean. So we call that Z, and it's just our data value minus the mean, so our distance, and then we cut our distance into standard deviations. How many standard deviations is that away? Is that deviation? So the formula is important because often we're going to have decimals and so forth. So we have a mean of 68, and we have a standard deviation of 5.9. We might want to know how far is a 91 from average in terms of standard deviations. So if we do our Z-score, we take our data value minus the mean divided by the standard deviation. So 91 minus 68 divided by 5.9. So for this particular, let's say this is a test, if you made a 91 and the class average was 68 with a standard deviation of 5.9, you made almost 3.9 standard deviations above the mean. And it's above the mean because your value is more than the mean. Now let's use this same formula for a person that made a 57 on the test. So if a person made a 57, but the average is 68 with a standard deviation of 5.9, let's see how many standard deviations from the mean that person is. So 57 minus 68 is negative 11 divided by 5.9. So that's about negative 1.86. Normally we're going to go to 2 decimal places there. Notice it's negative. That's because that piece of data is below the mean. It's lower. And then 1.86 is just a multiple of how many standard deviations it takes to get from the mean down to 57. So if the standard deviation is 5.9, we would have to go 5.9, not just one time, but not quite 2. We would have to go that distance 1.86 times, or a multiple of 1.86. That's how far we would have to go to the left to get to 57. So hopefully that gives you a little bit of a clue on what Z means. It's just how far in terms of the standard deviation R values from A.